Our next talk is by Shihan Kanungo, who will tell us about product formulas of Guillera and Sondow. And how would you like people to ask questions?
You can just like probably just unmute and say it at any time you want. Um, that'd be fine with that.
Okay, go ahead.
Yeah. So hi, I'm Shihan, and I'll be talking about a class of infinite product formulas. So first, I'm going to introduce the kind of product formulas we'll be looking at, then some background on the zeta function, and then finally the new results and the proofs. So I'll start with this result called Euler's product formula. Um, It's, as you can see, you can express sine of pi x as this infinite product, as shown. Now, there are actually some very nice intuition about why this should be true. So if we consider like for a normal polynomial, we can express it as a product of x minus its roots. And that's essentially what this formula is doing. Because sine of pi x has the roots is just the natural numbers because sine of any multiple of pi is 0. So this expression on the right is essentially the same thing as what we do for a normal polynomial. Now, if we substitute x equals 1/2 into this product formula, then since sine of pi over 2 is equal to 1, we get the following. So if we substitute x equals half into this, we get this expression here. And now if we just rearrange this and factorize each of these terms, we get this very cute product formula called the Wallace product. And I think this is is quite pretty to look at. And these kind of product formulas is what we're going to be looking at today. So Guillera approved this more complicated product formula for E, Euler's constant. And the pattern in the terms here is a little bit harder to see. But if you look at it for a little while, you'll see that, well, the exponents are just 1/1, 1/2, 1/3, and so on. And in each term, the bases of each of these factors go 1, 2, 3, 4, 5, and they alternate. And the exponents are just binomial coefficients. So explicitly, the nth factor in this product is the nth root of this number that I'll call Tn, which is the product from k equals 0 to n of k plus 1 to the -1 to the k plus 1 times n choose k. Now, what is very interesting is that Jonathan Sondow proved this formula, which is extremely similar. And the only difference is that the exponent, instead of the nth root, it's the n plus 1th root. And on the left-hand side, we have e to the gamma. And gamma is the Euler-Mastroianni constant. And it is a pretty important constant in number theory. It's unknown whether this constant is irrational or rational. And that's a pretty big open question. And on the left, that's the definition of gamma. And it's surprising that if we take this formula and then we just change the exponents by like 1/n to 1/n plus 1, we get something that looks very similar. Now, a very natural question to ask is what comes next? If we, instead of 1/n, we do 1/n plus 2, and the bases are still the same. Now you could suspect that maybe it's like something e to the gamma squared or something like that. However, it's something completely different. It's the square root of 2 pi over e. And the gamma has completely disappeared, and now we have a 2 pi. So it looks very different. And if we go one more step further, we get a more complicated expression. And here A is another constant, the Glaisher-Kinkelin constant. I will talk about this later on, but another important constant in number theory. So now we have these 4 numbers, which are all generated by the same kind of product. but there doesn't seem to be any natural pattern at all. Um, so that's what this product formula is what I'm going to be talking about and how we can evaluate it. So now we need to talk about the Riemann zeta function because it turns out that this is very intimately related to the zeta function. So this is probably the most important function in all of number theory. And it's defined as the series zeta of s is equal to 1/1 to the s plus 1/2 to the s plus 1/3 to the s, and so on. Now, this series doesn't necessarily converge. For s greater than 1, or for the real part of s greater than 1, it does. However, since this is like a talk, and I'm not going to really care about convergence at all. We also know I'm just going to tell you that you can define this on all of C by something called analytic continuation. And actually, this is not quite true. At s equals 1, we have something called a pole, where zeta is unbounded. And that turns out to be important later on. Now, this is not the only way to define zeta of s. We can also express it as this product over prime numbers. This is called the Euler product. And the reason that these are equal is that for every term 1/n to the s in this sum, we can look at the prime factorization of n, and then like map the exponent of the prime corresponding to that prime factorization when we expand this product. But neither of these is actually the form of zeta of s that we will be using. A theorem of Haas shows the following expression. It says that zeta s minus 1 times zeta of s is equal to this sum. Now, why would this be related to our infinite products? So recall that we defined Tn to be the term of the product, as shown. And then if we said z alpha, where alpha is some parameter, to be the product of the 1/n plus alpha plus 1 roots of Tn, that is basically the infinite product we're looking at. If alpha equals 0, -1, sorry, then it's the Guillera product, which is equal to E. And if alpha equals 0, then it's e to the gamma. Now, these at first don't seem that similar, but the first thing we can do if we want to try to make z alpha look like this is turn all these products into sums. And to do that, we can just take the log. So if we take the log of z alpha, we get the following expression, which already is starting to look very, very similar. The only differences are there's an alpha here, and instead of a k plus 1 to the 1 minus s, there's a log of k plus 1. It turns out that you can actually make these almost the same. Like we can make these two terms the same by taking the derivative of this. So if we note that the derivative of k plus 1 to the 1 minus s with respect to s is negative log k plus 1 times k plus 1 to the 1 minus s, then if we evaluate this at s equals 1, this term goes away, the k plus 1 to the 1 minus s term. So that means that the log of z alpha is just the derivative of with respect to s of this sum at s equals 1. And now this sum is the same as this sum, except there's an alpha here. If alpha equals 0, then they're exactly the same. So we get that log of z0 is the derivative of s minus 1 times zeta of s at s equals 1. So now we can go further and just evaluate this derivative. So if we use the product rule, then the derivative of s minus 1 times zeta of s is zeta of s plus s minus 1 times zeta prime of s. Now, remember how I said that zeta of s was undefined at s equals 1. So that might be a problem. However, it turns out that we can actually deal with this in the following way. So zeta of s has a Laurent series, which is essentially like a Taylor series, except we allow negative exponents as well. So this is the Laurent series for zeta of s. C1 and C2 and so on are just constants that are unimportant. Their values are unimportant. As you see, if we plug in s equals 1, we have a 1/0 term, which is the unbounded part. Now, if we take the derivative of this expression and multiply by s minus 1, then we get this 1/s minus 1 becomes negative 1/s minus 1. the gamma goes away, and all of these terms stay similar. Like Cn becomes n times Cn. Now, when we add these, the 1 over s minus term gets canceled. And if we plug in s equals 1, all of these terms are 0. So we just get a gamma. So it turns out that the unboundedness of this function and this function sort of cancel each other out. And that means that we get log of z0 is equal to gamma. And that proves the e to the gamma formula that we saw earlier. So this is the proof of the Sondow's formula, z0. But what would be the general expression for higher values of alpha? Because we can't directly apply the theorem there. So that's what the new results that we proved are going to tell us. So first, we need to talk about the Stirling numbers. So we're going to be using the unsigned Stirling numbers of the first kind, and it's denoted with these square brackets. And they have many different definitions. There's a combinatorial definition, which is the number of permutations of 1 through n that have exactly k cycles. This is going to be unimportant for us, actually. There's also recursion, which we have some initial conditions. And then we have something very similar to the binomial coefficient recurrence, except there's an extra n. And finally, there's an algebraic definition, which is it's the x to the k coefficient in the rising factorial. So the rising factorial is x times x plus 1 times dot 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 times x plus n minus 1. And it's x to the k coefficient here. So now these two definitions are what we're gonna be interested in. So now in the main theorem, first define capital Z alpha to be that sum that we saw earlier. And the log of the Z alphas, little z alphas, is going to be the derivative of this capital Z alpha at s equals 1. So if we evaluate this guy, then we evaluate this. So in our main theorem, we explicitly evaluated both of these the ZDs in terms of the Riemann zeta function. And this is for integer d greater than or equal to 0. And if we look at this expression over here, and then we compare it to this guy over here, you'll notice that it's the same thing, except instead of x to the k, we have some function of k. So it's like we take the rising factorial polynomial and then replace the x to the k term with this. And before we discuss the proof, I would like to show you an example of how we can use this to compute one of the ZDs. So if we look at Z1, which is the simplest example, then we plug in the formula. Then since 1 Stirling 0 is equal to 0, there's just one term, and that becomes zeta of 0 minus zeta prime of 0. However, we can both of these values are known, so we can just plug in those known values, and exponentiating that, we get z1 is equal to the square root of 2 pi over e. So I could also show you how to do it for z2 and so on, but it's extremely messy, and we have a bunch of those computations in our paper, but they're not very fun to read. So now we'll discuss the proof. So the proof is there's 3 parts. First, we show a lemma, then we show a functional equation that we use to prove the main theorem. So this lemma doesn't have any zetas or infinite products or anything like that in here. It's a pretty simple statement, as shown. Now this lemma has like a boring proof, and it has a very fun proof. And obviously, I'm going to talk about the fun proof. To do this, we let delta be the forward difference operator. So delta of a function f of v is defined to be f of v plus 1 minus f of v. And one property of this forward difference operator is that if we iterate it n times, we get on a function. So that if we apply this operator n times, we get the following expression, which is very similar to this. So if we were to rewrite this expression in terms of the forward difference operator, what we would get is that it's the sum from n equals 0 to infinity of a -1 to the term, n term, because here it's -1 to the n minus k, and here it's -1 to the k, times a delta to the n of v to the 1 minus s. And here we define v to be u plus 1. So now we have a much simpler expression. And now the fun part is we look at just this part of the expression. We forget about the v to the 1 minus s for now. And then this, everybody knows that you can write this as 1 over 1 plus delta, which is equal to 1 plus delta inverse. And obviously this doesn't look like you're allowed to do this because delta isn't a number. But there's a way to formalize this such that you can actually do these kind of operations. And now 1 plus delta is, if you compute it, it just sends f of v to f of v plus 1. So 1 plus delta inverse should just send f of v to f of v minus 1. And then this means that this expression is just 1 plus delta inverse of v to the 1 minus s, which is just v minus 1 to the 1 minus s, which is u to the 1 minus s. So that is, I think, a pretty slick proof of this identity. Now, the next step of the proof is this functional equation. So it expresses z alpha of s in terms of the values of z alpha minus 1 of s. And I'm not going to go into the full proof, but the sketch is that in the definition of z alpha of s, we have some binomial coefficients. And if we apply this identity, binomial coefficient identity to these binomial coefficients, it splits into two different sums. And one of the sums is essentially z alpha minus 1, and the other one of s minus 1. The other one is this. But there are some extra terms that have to be taken care of. And it turns out they have exactly this form. And the lemma will just kill them all. So that's how you prove this functional equation. So then once we have this, if you notice, it does look pretty similar to the recurrence for the Stirling numbers. Let me find that. Yeah, this one over here. And that makes sense because we're trying to prove that they can be expressed using these the Stirling numbers. So that's exactly the idea of the last part of the proof. So we want to show that capital ZD of S is equal to this. And the idea is that we induct on D. Recall that we proved the D equals 0 case in the beginning. And then using the functional equation and applying the recurrence formula for the Stirling numbers, we can prove the next step. So here's all the algebra. We write ZD of S in terms of ZD minus 1. Then we plug in the induction hypothesis onto these two functions. Then we can group the like terms together. And then we get the Stirling number recurrence. And then that gives us the formula. And then finally, we will, to get our actual infinite product, we need to take the derivative of this at s equals 1, which gives us the final formula. So now once we have this, you may ask, okay, we can write this product in terms of the zeta function, but can we explicitly evaluate it like we did for like e to the gamma or square root of 2 pi for e? And we can sort of do this. So the values of zeta of 1 minus k and zeta prime of 1 minus k for integer k we can explicitly evaluate these in terms of some constants. So if we actually do this, then we get this kind of nasty looking corollary, which explicitly evaluates all of the ZDs. So this part is fairly straightforward. But we have three new constants over here. So we have h2k, which are just the harmonic numbers. So 1 over 1 plus 1 half plus dot 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 plus 1 over 2k. B2k are the Bernoulli numbers. These are also rational numbers. They're pretty important, and I'm not going to define them here because that would take too much space. And finally, the AK. These are the Bendersky-Adamczyk constants. These are much more hard to deal with than the other two. And so these actually generalize the constant A, the Glaisher-Kinkelin constant that was in the very beginning. And here I'll talk about the definition of these constants now. So Stirling's formula for the factorial says that n factorial grows roughly as square root of 2 pi times n to the n plus half over e to the n. Now there's also a similar formula for the hyperfactorial, which is defined to be 1 to the 1 times 2 to the 2 times 3 to the 3 and times so on. And it turns out that it grows roughly as a times n to some polynomial over e to some polynomial. And a is the Glaisher-Kinkelin constant that I mentioned earlier. Now, if we look at the number square root 2 pi and a, these do seem familiar because they were appearing in our evaluations for the infinite products. And yes, that is indeed what happens. In general, we have 1 to the 1 to the k times 2 to the 2 to the k and so on, grows as ak, the Bendersky-Adamczyk constants, times n to the some polynomial over e to the some polynomial. And these constants are also very closely related to the zeta function. So it turns out that the log of these constants, it can be expressed in terms of the zeta function and its derivatives. And this is exactly why they appear in that explicit form above. So yeah, that's all I wanted to talk about. This is the paper where that this is based on. And I would like to thank my mentor, Dr. Jordan Schettler, for his guidance throughout when we're working on this project. I'd also like to thank Wadam Zudulin, Jeffrey Lagarius, and M. Ramarti for their encouragements and suggestions on our paper. I'd also like to thank Euler Circle for giving me this opportunity to present. And finally, I'd like to thank my parents. Thanks. Does anyone have any questions?
Okay, so if there are no questions, then thank you.